right, significance test for a difference of proportions. All right. For all of these, you're going to set up your null that the row from population 1 or treatment 1 equals the row of population 2 or treatment 2, or you can say that the difference between the treatments is 0. The difference between the two populations is 0. But there's an interesting thing that happens here, because if the null is true, then everyone in the sample came from the same population. Then, like, if the two treatments are the same, then is p hat 1 and p hat 2 actually supposed to be different, or are they actually just lumped in together where there would just be this many successes and this many failures on average? Okay, if the two populations are the same, are the percentage of people in this group who smoke and the percentage of people in this group who smoke actually different, or is it just that's the average of them is the percentage of people who smoke? And so we use a combined p hat combined sample proportion to create our standard error. So rather than using p hat 1 and p hat 2, we actually use p hat combined. P hat combined. Okay. And where does that come from? It's all successes out of all individuals. Okay. So you take your successes from both, add them together, your totals from both, add them together, and you get this nice little formula that you can either, it looks just like the other one, but rather than it being P1 hat and P2 hat, if those are both technically the same, let's just combine them and get a new P hat combined, okay, over the two things, which then would look like this if they're actually just different, okay? If they have different sample sizes. That's just factoring out the numerator. Since they have the same numerator, they factor it out to the left. But it's really, this formula is identical to the one that we use for confidence intervals, except for we use this p hat combined, which is rather than x1 over n1 here, okay, it's x1 plus x2 over n1 plus n2, and we get the same, and it ends up being some proportion in the middle of the two, especially if they have equal sample sizes, then it's exactly in the middle. But that's the weird thing for this. Guess what? Your calculator does it automatically, and so you don't even have to worry about it, okay? But it is a subtle difference that we do when we do a test for a difference of proportions, because if we assume they're the same, then let's actually treat them that way. That's the reason why it happens, okay? So to test the hypothesis that the rows are equal, we take the difference in our samples, which is basically minus this 0 here, since they're equal. If I subtracted the difference between the two of them, it would be 0, okay? And then we take this p hat combined and q hat combined, 1 over n1, 1 over n2. Guess what? Your calculator does it, okay? And remember, if the alternative is that the first treatment is greater than the second, we're looking for a norm CDF to the right of Z. If it's that the first treatment is less, we're doing a norm CDF to the left of Z. And if it's that they're not equal, we're looking for the two sides, and you get double the p-value. You get the below plus the above, okay? Our conditions, nothing too new or creative here. Simple random sample or two groups in a random experiment, okay? Normality, everything. It says at least 10, but it says you can just let it be at least 5. We see that at least 5 again. And it talks about like, it's kind of conservative, but okay, it can be 5, okay? And we use p hat combined. So it's the sample size of 1 times the p hat combined and q hat combined. So it's a little bit different than just the counts. And then independence, the samples are independent of each other, and the two populations must be at least 10 times as large as their samples, okay? So nothing new there except for this weird p hat combined that we need to work with in all of these places, okay? And this is just for the tests, because the tests assume that P1 is equal to P2, in which case even the fact that P1 hat is not equal to P2 hat, we lump all the successes together out of all the trials together, because if the null is true, then we shouldn't separate them out and treat them differently, okay? And it really allows us to use this measuring stick that's more consistent, okay? So what happens? Let's try one. So high levels of cholesterol are associated with higher risks of heart attacks. In Helsinki, Finland, they tested a bunch of middle-aged men randomly assigned to either take the drug gemfibrozol to reduce their cholesterol, and 2030 took a placebo. And then during the next 5 years, they measured how many had heart attacks. All right. So here are the sample proportions we see right here. The P parameter is the true difference in heart attacks of gemfibrozol minus placebo. Okay. All right. The true difference in proportions of heart attacks in those two groups. Hypothesis, the null is that rho gemfibrozol equals rho of placebo, okay? And the alternative is gemfibrozol is actually having fewer heart attacks than placebo. Assumptions and conditions, random. Yes, they were randomly assigned. Independent, I'm guessing that there are more than 40,000 men who have high blood pressure in Helsinki area, okay? And normal, all of these, if we did our p-hat combined, it's basically 56 plus 84 over 2051 plus 2030, but it's basically going to be about 56, about 84, which are all way greater than 5, okay, times each n. And the Q hat combined would be just the complement to this times each n. And all of those need to be at least 5. Okay? If you run your test first, you can then just get the p hat combined off your calculator and go back and fill these in. Okay? Name the test. We have 2 samples. And it's a Z test for proportions. Okay? The test statistic, I don't want to calculate this by hand or obtain a p-value by hand. That's why you grab your calculator at this point. And when you grab your calculator, you say stat tests, and now we're doing a 2-prop Z test. So I'm going to hit number 6. I've already entered the data, 56 out of 2051 and 84 out of 2030. And we're expecting mu1. We want evidence that, or proportion 1, the proportion of people who have a heart attack with the gemfibrozol is less than the proportion of people who have a heart attack with the placebo. And that's our Z-score. That's our test statistic, negative 2.47. And that's our p-value, James Bond, 0.007. And notice we get a P1 hat, a P2 hat, and this P hat is the P hat combined, 0.034, okay? And so I could use that times N1 and N2, and then 1 minus it times N1 and N2, and I would get my numbers that all need to be at least 5. So negative 2.47, okay? And my p-value equals James Bond, and so we make a decision, okay? Since my p-value equals 0.007 is less than 0.05, which is my alpha. Oh yeah, by the way, alpha equals 0.05. All right, we reject the null that gemfibrozol and placebo have equal proportion of heart attacks, okay? There is sufficient evidence to suggest that gemfibrozol reduces heart attacks. Sweet! That was the whole goal of the experiment, okay? That is chapter 13, folks. So, good luck and farewell.